Hello dear learners, welcome you all to the fourth week of the course on electricity and electrical wiring. The previous week modules dealt with magnetic properties, magnetic hysteresis and certain magnetic circuits. This module of week 4 deals with the fundamentals of alternating current. This module includes 3 sessions. They are alternating current and its production part 1, alternating current and its production part 2, and different components with AC. In this lecture, we will focus on the alternating current and its production, which contains what is AC current, representation of AC waveform, basic parameters of AC, types of AC waveform, different values of AC voltage and current, form factor and peak factor, phase and phase difference, Phasor and Phasor diagram. So what is an AC current? AC current is one whose magnitude varies continuously and reverses the polarity periodically. So here you can see, in case of DC circuit, current flows only in one direction. But in case of the AC circuit, current reverses periodically. So that's the basic difference between AC current and DC current, or AC current source and DC current source. In case of AC current sources, the magnitude of current varies continuously with time. The polarity reverses periodically. It has certain frequency of oscillation, and this is a symbol of AC source. For any kind of AC source, we go for using this symbol. This is how we represent AC current. In case of DC current, a straight line which is parallel to the x-axis is used, while in case of representation of a AC current, normally a sinusoidal wave is used. So this figure represents an AC current and a DC current. So here you can see the DC current can be simply represented by a straight line which is parallel to the x-axis. But in case of AC current, a sinusoidal wave actually represents an AC current. So if we place a coil rotating in a magnetic field, it can induce an EMF which varies sinusoidally with respect to time. Such an EMF leads to a sinusoidally varying current with time, and this is known as the alternating current or AC current. Let us discuss few basic parameters which describes AC current properly. For example, the cycle. So a complete oscillation of the AC waveform includes both a positive and a negative half. It is not measured in units, but it refers to a full up and down movement in the wave. Secondly, amplitude. The maximum value of current or voltage in an AC waveform, it may be either positive or negative, is termed as the amplitude. Amplitude in case of current is measured in amperes, and in case of voltage it is measured in volts. Next we move to another parameter which is important for AC waveform, that is the frequency. The number of complete cycles of the AC waveform that occur in 1 second is termed as the frequency. The unit for frequency is hertz. The next parameter that we want to discuss is the period. What is a period? The time it takes for one complete cycle of AC waveform is termed as the period. The unit for period is seconds. The alternating voltages and currents can have different waveforms or wave shapes depending on the specific application, design, or the source. These waveforms are obtained by plotting the instantaneous values of voltage or currents as the ordinate against time as the abscissa. The main types of AC waveforms are the sine wave, square wave, triangle wave, sawtooth wave, trapezoidal wave, complex wave, half wave rectified wave, and full wave rectified wave. We will discuss this wave one by one. The most common and ideal form of AC is the sine wave. So here you can see the sine wave. So it is a very smooth curve which represents the alternating current. The most common and ideal form of AC is the sinusoidal wave. It follows a very smooth and continuous oscillation which rises and falls symmetrically. Here you can see the current or voltage rises symmetrically, it again falls, again it goes to 0 and then becomes maximum in a negative direction, then again it rises up like this. So in case of sine wave, the frequency and amplitude can vary. So this kind of sine waveforms are basically used in power distribution systems and in also our household power supplies. The next type of waveform is the square waveform. So in case of square wave, it switches abruptly between two levels, high and low. So it is a non-sinusoidal waveform with sharp transitions. High frequency square waves are used in digital circuits, clocks and plus width modulators. They have significant harmonic content which can lead to distortion in certain applications. The next type of waveform is a triangle waveform. As you can see the figure, it is like a triangle. So in case of triangular waveform, it has a linear rise and fall creating a triangle like shape. It is a periodic signal with equal rise and fall times. So this kind of waveform find applications in audio synthesis, audio oscillators and testing equipment, etc. The next type of waveform is said to be sawtooth wave, which is to some extent similar to the triangular wave. So here the waveform linearly rises or falls and then sharply drops or rises, forming the shape of a sawtooth. This kind of sawtooth waveforms are used in signal processing and certain music synthesis. There is a kind of waveform which is said to be trapezoidal waveform. In case of trapezoidal waveform, as you can see, it features the linear rise and fall times with a flat top resembling a, in case of trapezoidal waveform, you can see it features the linear rise and fall times with a flat top which resembles a trapezoid. Here the transitions are slower compared to the sharp edges of a square wave. This kind of waveforms are used in motor driving systems and analog signal processing. There is some kind of waveform where there is a combination of multiple sinusoidal and non-sinusoidal waveform. So this kind of waveform is said to be a complex waveform. Here we can see some part is sinusoidal while the other part is not sinusoidal. So it is not a completely sinusoidal waveform, but it is a combination of sinusoidal and non-sinusoidal waveform. So this kind of waveforms are used in audio waveforms and communication signals. So another kind of waveform is the half-wave rectified waveform, where the positive cycles are there but negative cycles are not there. Or we can say the negative half cycle is clipped off, leaving only the positive portion of the sine wave. So this kind of half-wave rectified waveform are used in simple AC to DC converters. Next we have the full wave rectified waveform. In case of full wave rectified waveform, the rectifier rectifies both halves of the AC cycle, inverting the negative portion to become positive. So this kind of waveform find applications in efficient AC to DC power supplies. In the next portion, we are moving to discuss about different values of sinusoidal voltage and current, because sinusoidal waveform is the most important and ideal for any kind of AC applications. So in case of sinusoidal wave, so this is a sinusoidal wave. Here whenever we say instantaneous value, the instantaneous value of current is that current which exists at any instant of time measured from some reference point. It can have any value from the minimum to maximum in the positive direction or in the negative direction. Mathematically, the instantaneous value of current is given by this equation. I is the instantaneous value of current, I subscript m. This is the maximum current in the AC circuit. Sin theta, theta is nothing but omega t. Theta shows the phase, and this is how the instantaneous value of current is connected to time period and maximum value of current. So in this figure itself, we can see that this difference between the maximum positive value and maximum negative value is termed as the peak to peak value of current or voltage. Next, we are moving to another kind of parameter which is used in the AC current or voltage, that is the peak value or maximum value. So peak value or maximum value is the highest value reached by current or voltage in one cycle. So here we can see the maximum value here is this one in the positive direction, and in the negative direction this is the maximum current. So that is the maximum or peak value of the AC current. In case of sinusoidal waveform, the positive peak value is equal to the negative peak value. So here we can see in this figure, so at 90 degree or the time period of T by 4, we are getting the maximum value of current in the positive cycle. Similarly, at 270 degree or the time period of 3T by 4, we get the maximum in the negative cycle. The other parameter which is used in AC is the peak to peak value. Peak to peak value is the sum of positive peak and the negative peak values, usually written as PP value. So if the maximum current is 1 ampere in the positive direction and maximum current is 1 ampere in the negative direction, then the peak to peak value can be 1 plus 1, 2 ampere. It is obvious that the positive and negative peak values cannot occur at the same time and may not have the same value in all kinds of waveforms. Next, we are moving to root mean square value. Root mean square value is also called the effective value. It is the value of current or voltage at theta equal to 45 degree, which equals 0.070 times the maximum current or 70.7% of the maximum value of current or voltage. The relation between the root mean square value and the maximum value is this one, that is I equal to Im divided by root 2. So we should understand that whatever value of an AC voltage or current is stated, it actually refers to the RMS value unless stated otherwise. If it is not mentioned, we should understand that whatever value of an AC voltage or current is stated, it actually refers to the RMS value. Usually, AC voltmeters and AC ammeters are calibrated to read RMS values. So, we see that the relation between maximum current and the RMS current is this one. Again, the relation between the peak value and PP value is this one. PP value is equal to 2 times the peak value. So, if we put the peak value or maximum value here, then we see that the relation between PP value and RMS value becomes this one. So, in the figure you can see the relation between the different types of currents and voltages used in AC. So, this is the maximum current that can be obtained in the AC waveform. So, if we consider the maximum current or voltage to be 10, in that case 7.07 of that will be the RMS value and 6.37 will be the average value. Let us now discuss what is average value of current and voltage. So average value is the arithmetic average of all the instantaneous values in one half cycle of the wave. For symmetrical sine wave, one half cycle is taken because for full one cycle the average would be 0. However, for non-symmetrical waves, it is essential to take the average value over one full cycle. If we take average of all the instantaneous values, suppose for in case of positive half cycle of the wave, the value comes out to be 6.37% of the maximum value. Therefore, the relation between the maximum current or maximum voltage and the average voltage or average current is this one. I average is equal to 0.637 into the maximum value, or we can say the average current is equal to 0.637 times of the maximum value. In case of this sinusoidal wave, we can see the relations between maximum value, RMS value and average value. Here we can see the maximum value is 10 and its RMS value is 7.07 and its average value is 6.37. Let us now discuss the form factor and peak factor in case of AC current. Form factor is defined as the ratio of RMS value of current and average value. So the ratio of RMS value and average value is termed as the form factor and it comes out to be 1.11. In case of crest factor or peak factor, it is the ratio of maximum value and RMS value. So it comes out to be 1.414. Next we are going to discuss about the phase of an AC current. The fraction of a cycle or time period that has elapsed since an AC current or AC voltage last passed a given reference point is called its phase. The phase may be expressed in different forms, like it can be expressed as the time measured in seconds, the fraction of time period, angle expressed either in radians or in degree. For example, here you can see in case of this sinusoidal wave at point A, the phase is pi by 6 radian or 30 degree. In terms of cycle, it is 1/12 of the cycle or t by 12 seconds. So since our time is 1 by 50 seconds, so therefore the phase can be 1 by 600 seconds using this one. Similarly, if we look at the phase at the point E, at point E the phase is 2 pi or it is 0 degree, or you can say it is the one complete cycle, or we can say it is the 1 by 50 seconds. The phase difference between two alternating quantities is more important than their absolute phases. So in this figure we can see two sinusoidal waves are moving in the same direction. One is A, one is B, where A is ahead of B by a phase of pi by 6. Similarly, if we look at this one of two sinusoidal waves A and B, we can see that A is moving ahead of B by a phase of pi by 2. So therefore, instead of phase, the difference of phase between two waves are more important. So here we can see that waves A and B, these two sinusoidal waves, they are completely in phase with each other. They are moving together, they are starting at the same point, while here, though they are starting in the same point, but they are completely out of phase with each other. Next we are moving to the AC wave equation. So let us consider two sine waves A and B which have same amplitude and same period. Let us consider A to be the reference and B is lagging behind by some phase. So the equation for A will be this one. and since B is lagging behind by a phase of phi, so the equation for B will be this one. Similarly, if we consider that B is going ahead of A, considering A as the reference point, we can write the equation for A is this one, and since B is going ahead of A by a phase of phi, so this will be the equation for B. In case of AC wave equation, a plus sign is used in the connection with a phase which denotes the lead, while a minus sign means the lagging of the phase. Let us now discuss what is phasor and phasor diagram. A phasor is a rotating factor that represents a sinusoidally varying quantity. It can be the sinusoidally varying current or it can be sinusoidally varying voltage. The length of the phasor is equal to the peak value of the oscillations, and the angular speed is equal to the angular frequency of the oscillations. And the phasor diagram shows the magnitude and phase of a phasor and the relationships between multiple phasors. It means the relationship between a current vector and a voltage vector can be obtained using the phasor diagram. The length of the phasor represents the magnitude and the direction of the phasor represents the phase angle. Dear learners, hope you have enjoyed this session. Here we have a small quiz. You can try this. Let us solve some problems on fundamentals of AC. The first question is, a sinusoidal alternating wave current having a frequency of 50 Hz has a peak value of 10 ampere. What would be the value of current after 1/300 seconds from 0? So how to solve this problem? To solve this, so the current equation is this one, where I is equal to Im sin omega t, where Im is the peak value or the maximum value, omega is the angular frequency, t is time. So we know omega is equal to 2 pi f, f is the linear frequency. So here our frequency is mentioned to be 50 Hz. So we are putting the value here. So it is given that t is 1/300 second from 0. F is frequency is 50 Hz and the maximum value of current is 10 ampere. So if we put the values here in the equation, then the answer for current after 1/300 second from 0 comes out to be 8.66 ampere. Okay, so let us go for another question. In the second question, it is given that an alternating current is represented by this equation. So we have to find the frequency, RMS value and average value of this AC waveform. So this is the standard equation for AC wave. So if we compare this standard equation with the given equation, then we find that the maximum value of current to be 141.4. We have to go for finding the frequency, RMS value and average value. So the frequency 2 pi f. So here the frequency is, we can go for finding the frequency from this, from 628. So from, if we compare these two equations, we see that 2 pi f is equal to 628. Therefore, frequency f is equal to 628 divided by 2p. Therefore, the frequency f is equal to 628 by 2 pi. So the answer is 100 Hertz. Okay. So if we go for finding the RMS value, the relation between RMS value and maximum current is I equal to Im by root 2, where Im is the maximum or peak current. So here maximum or peak current is 141.4 ampere. So if we put the values, then it comes out to be 100 ampere. The next value that we have to find is the average value. So we know the relation between average value and maximum current, and from this relation, by putting the value for maximum current, we can find the average value of current to be 90 ampere. So dear learners, hope you have enjoyed this session. So in this session, we have learnt about the different fundamental parameters of AC wave, different types of AC waveforms, the phase and phase differences, how to draw a phasor diagram. Thank you for your attention. In the next session, we will meet with a new topic.